And then we have this theorem that looks like a zigzag shape. There are two theorems that form a zigzag shape, but the other one involves the center, where the angle at the center is 2 times the angle at the circumference, and we've already covered that. However, this zigzag over here does not involve the center. The points concerned are at the circumference. So for this theorem to exist, point A, point B, point C, and point D need to touch the circumference. Now, if point A and B have touched the circumference, and point C hasn't, and point D has, the theorem is not existent. If one of these 4 points hasn't touched, the theorem is not existent. So it won't be existent to the other 2 that have touched when the other 2 hasn't touched. No, it doesn't work that way. So please ensure that all points have touched the circumference. If they have touched, angle A will be equal to angle B, and the reason will be angles in the same segment, or angles subtended by the same arc. But I'll use the first reason, which is angles in the same segment. And again, angle C is equal to angle D. It's the same. And the reason is angles in the same segment. And that right there is our theorem. But make sure that you understand that point A, point B, point C, and point D have touched the circumference. Because if one of the 4 points haven't touched, the theorem is non-existent. And the zigzag shape does not have to look as perfect as we see, even if it's a strange looking zigzag. As long as all 4 points have touched the circumference of the circle, the theorem exists. And speaking of strange zigzags, look what we have here. But the great thing is that all 4 points touch the circumference. And so there's a theorem in this case. And so angle C will be the same or equal to angle D. And the reason is angles in the same segment. And angle A will be equal to angle B. And again, the reason will be angles in the same segment.